So in the last video we have defined what is meant by maximal ideal, and then we have seen some problems based on maximal ideals. Now we will define prime ideals, right? So in this video this is based on prime ideals. Right? So prime ideals. So first we will define what is meant by prime ideal, and then we will see some theorems and problems based on prime ideals. So prime ideal, so let R be a ring. Let R be a ring, S be an ideal, S be an ideal of R. So you know what's the ideal? So ideal means first it has to be subgroup, and then it has to be left ideal as well as right ideal. That is AR and RA belongs to S. If R belongs to R and S belongs to S, so S be an ideal, then this S will be maximal ideal. Then S is said to be prime ideal. S is said to be prime ideal. So maximal ideal you see defined in the previous video, and ideal is said to be maximal ideal if there is no other ideal that properly contains this ideal. So now we will define prime ideal. Then S is said to be prime ideal of R if AB belongs to S. Suppose if AB belongs to S, this A comma B belongs to R. This implies either A belongs to S or B belongs to S, right? So you are taking two elements in R and you are making AB, and if that belongs to S, then one of them should be in S. Then we say that ideal is prime ideal for all A comma B, right? This is why either yes. So what we are doing is we are having R, and here we are having S, and what we are doing is here we are taking two elements A, B, and you just operate A with B, and if you get these elements belongs to S, then either A has to be in S or B has to be in S. One of them should be in S, then only you will get AB belongs to S. So if that happens, then this S is said to be a prime ideal. So maximal ideal means if there is some other ideal, suppose let us say let us recall the definition of maximal ideal. Let us say this ring R, let us say this is our M. So this is an ideal, and this ideal said to be maximal ideal if there is no ideal properly contains U. This is not maximal ideal, because I can find, if suppose if U is another ideal, then you can see this U is properly contained in M. M is properly contained in U. Therefore this M is not maximal. So this is said to be maximal ideal if there is no ideal which properly contains M other than R. Surely R will always contain every ideal. Suppose this M is said to be maximal ideal if there is no ideal that properly contains M, right? That properly contains M. Suppose if there is some other ideal which properly contains M that is not equal to R, then M is not maximal ideal. Now so we have defined prime ideal. So let R be a ring and S be an ideal. Then this S is said to be prime ideal of R. You are taking two elements in R. If AB belongs to S, then one of them should be in S. So if that happens for all AB, then the ideal is said to be prime ideal. So maximal ideal means if there is no other ideal other than R that properly contains M. M is said to be maximal ideal if there is no other ideal properly contains M other than R. So we will give some example. In the ring of integers, the principal ideal 7 is a prime ideal. That is, if you take R to be equal to the integers, then the ideal generated by 7 is a principal ideal. Why? So we know that in integers every element generated by itself is ideal. Every element you can generate an ideal. So what is the set? This set contains 0, plus or minus 7, plus or minus 14, plus or minus 21, etc. This is an ideal. If you for prime ideal, first it has to be ideal, then only you can talk about prime ideal. And for maximal ideal also, first it has to be ideal, then only you can talk about maximal ideal. So first you just verify that it is an ideal. So for ideal, what we do, there are two conditions. AB belongs to S means A minus B belongs to S, and left ideal as well as right ideal, which we defined earlier. Now you can see this is an ideal. right? This is an ideal. So for ideal, two conditions, A minus B should be belongs to S. If you take two elements, A belongs to S, B belongs to S, A minus B should be in S, and RA should be in S, and AR should be in S. Here R belongs to R, A belongs to S, right? So if these three conditions are satisfied, then the set is said to be an ideal. A subring is said to be ideal if these three are satisfied. If along with this, if AB belongs to S implies A belongs to S or B belongs to S, then this will be a prime ideal. This will be a prime ideal. Suppose if there is no other ideal, suppose if S is contained in, let us say S is contained in U and U is contained in R, this implies either S is equal to U or U is equal to R, then means this is a definition of a maximal ideal. So 1, 2, 3 only ideal, 1, 2, 3, 4 prime ideal, 1, 2, 3 and 5 is maximal ideal. So 1, 2, 3 is ideal, 1, 2, 3, 4 is prime ideal, 1, 2, 3, 5 is maximal ideal. Is maximal ideal. Now we have since a recap. Now you can see the ideal generated by 7. This is an ideal, right? For ideal, you just take two elements. For example, if I take 7 and 14, 7 minus 14 is minus 7 belongs to S. Therefore, A minus B belongs to S. And AR and RA will be belongs to S. If you take an element R, suppose for example, if I take R to be equal to 1, because R can be any element in the ring, integers. If I take S to be equal to, let us say it is 14. Now what about R into S? It is 1 into 14, which is 14, which belongs to S. And what about S into R, which is again 14 into 1, which is 14, belongs to S. So therefore it is true for any R and S. So therefore this is an ideal. Now this is also a prime ideal. Why? Now for what is the definition of prime ideal? AB belongs to S, A belongs to S, B belongs to S. This implies either A belongs to S or B belongs to S, right? Now AB belongs to S means what can I say about let us take two elements AB, then AB should be in S. AB should be in S. Now for example, if I take A to be equal to 7, B to be equal to minus 7, now what about AB? So AB is 7 into minus 7, which is minus 49, which belongs to S, because this set contains minus 49, which is a multiple of 7. So this means either A belongs to S or B belongs to S, which is true, right? You can see in this case both A and B are in S. In this case both A and B are in S. So for example, in the ring of integers, the principal ideal 7 is a prime. Obviously, if AB is in 7, then A or B must be multiple of 7. Now, this is a prime ideal. Now, what can I say about this ideal? That is an ideal generated by 6. So this set contains 0 plus or minus 6 plus or minus 18 and so on. Sorry. Actually, I'm making a mistake. So for proving this has to be ideal, AB belongs to S, A belongs to R, B belongs to R. I taken this to be in S. This implies A belongs to S or B belongs to S. This is a condition for prime ideal. Now we will prove that this set is a prime ideal. Actually, I made some mistake by putting S here. Actually, it is R. So AB belongs to S. If A belongs to R, B belongs to R, then this implies either A has to be in S or B has to be in S. Now let us take A to be equal to, AB belongs to S means either A or B is a multiple of 7. Because what S is this is our S. So S is the ideal generated by 7. So if some element belongs to S means one of them should be multiple of 7. So A or B is a multiple of 7. So surely either A belongs to S or B belongs to S. So it is natural, right? For example, if we take A to be equal to 1, B to be equal to 7, then we will have AB is 7 which belongs to S. So here you can see this does not belongs to S, but this belongs to S. So surely one of them should be in S. One of them should be in S. One of them should be in S, right? Yes. So AB is equal to 7, that belongs to S. So this is a prime ideal. Now what can you say about the ideal? What can you say about the ideal? 6. So this set contains 0 plus or minus 6 plus or minus 80 and so on. Now if AB belongs to S, A comma B belongs to R, this implies A has to be in S or B has to be in S. Is this a prime ideal? Is this a prime ideal? It is not, because if I take A to be equal to 2, B to be equal to 3, then you can see AB is equal to 6 which belongs to S. But either 2 is not belongs to S, 3 also does not belongs to S. This is not a prime ideal. So for a set to be prime ideal, if you just take 2 elements in R, if the multiple of that element belongs to S, then one of them should be in S. But here you can see this is not a prime ideal. If I take A to be equal to 2, B to be equal to 3, then AB is equal to 6 which belongs to S. But this also does not belongs to S, this also does not belongs to S. So therefore in integers, every ideal generated by P is a prime ideal. Is a prime ideal. So you can see this is a prime ideal because someone is a prime. Someone is a prime. And also this is not a prime ideal because 6 is not a prime. Right? So in the set of integers, an ideal generated by prime is a prime ideal. In the integers alone, the set of integers. Now we will prove the important theorem. Every maximal ideal is a prime ideal. Every maximal ideal is a prime ideal, but every prime ideal is not maximal ideal. That is not we need to prove, right? So theorem, we need to give a counter example to show that every prime ideal is not maximal. Sorry, every maximal ideal is a prime ideal, but every prime ideal is not maximal ideal, right? Yes. So let R be a commutative ring. Let R be a commutative ring with unity. Then every maximal ideal of R is a prime ideal, right? So let R be a commutative ring with unity, then every maximal ideal of R is a prime ideal. So we will prove this theorem that every maximal ideal is a prime ideal. Every maximal ideal is a prime ideal. Let R be a commutative with unity, then every maximal ideal of R is a prime ideal. Suppose if the ideal is maximal, then it will be prime ideal. It will be prime ideal. Again, you can give an easy counter example, right? So, okay, first we will prove this and then we will. Every maximal ideal of R is a prime ideal. So prove. Actually, we already know, right? We already know if R is, this is a theorem that we proved in the previous class. If R is a commutative ring and S is an ideal, S is a maximal ideal, X is maximal ideal, this implies R by S is a field. R by S is a field. This is the one important theorem in concept point of view, that this is a field. If R is a commutative ring and S is maximal ideal, then the quotient ring R by S is a field, right? Now every field is an integral domain. We already know, we know that every field every field is an integral domain, and every integral domain is not a field. Suppose if this integral domain is finite, then it will be field, right? Every field is integral domain, but every integral domain is not a field. Suppose if the integral domain is finite, that will be a field. For example, integers is an infinite integral domain which is not a field. So every field will be integral domain, but every integral domain is not a field, right? So suppose if the integral domain is finite, then it will be a field. So every field is an integral domain, we already know, right? So therefore, since R by S is a field, this means R by S is integral domain, because we know that every field is an integral domain, but every integral domain is not a field. You have to be very careful. So R by S is a field and R by S is an integral domain, right? Yes. So it's by theorem 1. Yes. Now this will be, actually this one theorem, R by S is integral domain if and only if S is prime ideal. S is prime ideal. It's a very important theorem that I will prove. Actually this is also a very small proof. You can refer page number 365. I'll repeat. If S is maximal, then X is maximal if and only if R by S is a field. Suppose S is prime ideal, actually maximal ideal, prime ideal if and only if R by S is an integral domain, right? So this theorem I have already proved. This theorem is a very easy theorem. That is, this proof is in 365. So page number 365 is very easy proof. So a prime S is a prime ideal if and only if R by S is an integral domain. R by S is an integral domain. Now we already know R by S is integral domain, so therefore we can conclude that S is prime ideal. So therefore I have assumed that S is maximal ideal, and then I have proved that S is a prime ideal. S is a prime ideal. So we will see some examples. So we will use an example. Maximal implies prime, but prime does not implies it is maximal ideal. Actually, again we can give an easy example that with along you can give an easy example with set of integers. So maximal ideal implies prime ideal. So prime ideal does not imply that it is maximal ideal. Maximal ideal implies prime ideal by easy theorem. By theorem, R by S is a field, every field is integral domain, so therefore R by S is an integral domain. R by S is an integral domain if and only if S is a prime ideal, so therefore maximal ideal implies prime ideal, but prime ideal does not imply maximal ideal. So we will use an example. So again we will take R to be equal to integers. Let us take a ring to be equal to integers with respect to multiplication and addition. This is a ring. Now let us take, actually it has to be prime ideal, but it should not be maximal ideal. It is not maximal ideal. So first it has to be prime ideal, it should not be maximal ideal. Okay. Okay, in integers every prime ideal is maximal ideal, I think. Okay. So actually in integers, so for example, if I take 7, then this is prime ideal. This is prime ideal. This is also maximal ideal also, because we cannot find another ideal which properly contains 7. Okay. So in integers, every prime ideal is maximal ideal. So we need to think of another ring in which prime ideal is not maximal ideal. Actually in integers, every prime ideal is maximal ideal, but there exists some ring in which every prime ideal is not maximal ideal. If you think of integers, then every prime ideal is maximal ideal, right? For example, if I take an ideal generated by 7, then this set contains 0, plus or minus 7, 14, etc. This is a prime ideal. Just now we have seen in integers an ideal is said to be prime if t is a prime number. So therefore 7 is a prime number, and you can easily verify that AB belongs to S, A belongs to R, B belongs to R. This implies either A belongs to S or B belongs to S. So you can see just now we have proved that this is a prime ideal, and also it is a maximal ideal also, because there is no other ideal which properly contains 7, which properly contains 7. For example, if you think of 14, then this set is 0 plus or minus 40 plus or minus 28, etc. So this set contains 14, 28, but it does not contain 7. So therefore, it does not properly contain 7. So there is no proper ideal which properly contains 7. So therefore, it is also maximal also. So in integers, every prime ideal is maximal ideal, but we need to think of some other ring in which every prime ideal is not maximal ideal. That we will come to later part. At the end of the video, I will give an example to show that every prime ideal is not maximal ideal. Now we will prove an important problem. Now we will prove a very important problem. So let R be the ring of real valued continuous function defined on closed interval 0, 1. Let R be the ring of continuous real valued. Let R be the ring of real valued continuous function defined on closed interval 0, 1. Let us make a set M, and this set consists of all those function in R, all those continuous functions which are in closed interval 0, 1. So that is, here R is set of all continuous function on closed interval 0, 1. I'm collecting all those continuous functions which belongs to C of 0, 1 that satisfies the condition f of 1 by 2 is equal to 0. Show that M is maximal ideal. Show that M is maximal ideal. So we need to show that this ideal is maximal ideal. So M is a set consists of all those functions which vanishes at 1 by 2. So for example, this function will be in x minus 1 by 2 will be in M, because if I substitute x to be equal to 1 by 2, then this will be 0. And similarly, x minus 2x minus 2 will be in actually 2x minus 1 will be in this function, because if we substitute x is equal to 1 by 2, it will be 0. So it consists of all those functions which vanishes at 1 by 2. So we need to show that this set is maximal ideal. So for maximal ideal, we need to show that there is no proper ideal which properly contains this M. But I am not going to prove that. I am going to use a fundamental theorem of ring homomorphism. So I am going to use a theorem that if we know that if F is a homomorphism from a ring R to R dash, then R by kernel of F is isomorphic to R dash or F of R, right? F of R. So this is the fundamental theorem of ring homomorphism. If R is a ring, if R and R dash are two rings, then R by kernel of F is isomorphic to R dash if F is an isomorphism, right? That is our theorem I am going to use for proving this theorem. Right? Yes. So if F is an homomorphism from R to R dash, R and R dash are two rings, then R by kernel of F is isomorphic to R dash. Yes. Now what I am going to do is, here I am going to define a function F from, okay, I need to show that this is a maximal ideal, right? I need to show that this is a maximal ideal. Okay, so what I will do is, so what we need to prove is M is maximal ideal. It's a very interesting problem. So M is maximal ideal. This is the one we need to show, right? M is maximal ideal. So for that, I am going to show that R by M is a field. R by M is a field. We know that M is maximal ideal if and only if R by M is a field. I am going to show what is our R. R is a set of all continuous real valued function closed, that is our R is C of 0, 1. Our M is the ideal, that is M. I need to show, I'm going to show that this is a field, right? This is a field. I need to show, I'm going to show that C closed set of all continuous function are closed to 0, 1 by M. That is, I'm forming a quotient ring R by M. Our R is set of all continuous function, it's a field. For that, I'm going to use, and what I'm going to do is, I'm going to use by fundamental theorem of ring homomorphism, by fundamental theorem of ring homomorphism, what I'm going to do is, I'm going to define a map F from closed interval 0, 1 to R, closed interval 0, 1 to the real number, and I'm going to show that I'm going to find R by kernel of F. By first, you suppose if F is homomorphism, I'm going to define a map F from C of 0, 1 to R by, I'm going to define a map like let us say it is theta, right? Let us say it is theta. Let us say I'm going to define a map theta from closed interval 0, 1 to R. I'm going to define a map like theta of F is equal to F of 1 by 2. This is the map I'm defining, right? So whatever the function, you take the function from closed interval 0, 1 and it substitutes the value F of 1 by 2. So this F of 1 by 2 will be in real number. This is the homomorphism that I am defining from closed interval 0, 1 to R. Now we will prove that it is homomorphism, right? So we will prove that it is homomorphism. So for ring homomorphism, we need to show it is, we need to verify two conditions. The first condition is theta of F plus G. So we will verify that is ring homomorphism for theta of F plus G. What is theta of F plus G? So it is nothing but F plus G of 1 by 2. F plus G of 1 by 2. So this is nothing but F of 1 by 2 plus G of 1 by 2, so which is nothing but theta of F plus theta of G. So therefore it satisfies the first condition. Now what about theta of Fg? It is nothing but Fg of 1 by 2. So this is nothing but F of 1 by 2 into G of 1 by 2, which is nothing but theta of F into theta of G. So therefore theta is a ring homomorphism. Right, so we have proved, we have defined a map theta from closed interval 0, 1 to R, defined by theta of F is equal to F of 1 by 2. Now, so we have proved that this theta is a ring homomorphism from closed interval 0, 1, that is set of all continuous functions in 0, 1 to R. Now what I am going to do is, I am going to use the fundamental theorem of ring homomorphism. So I need to show that R by M is a field, that is C of 0, 1 by M is a field. This is what I need to show, right? Yes. So we have defined a map like theta of F is equal to F of 1 by 2, and then we have proved that map is ring homomorphism. So therefore we have defined a map theta from closed interval 0, 1 to R, defined by theta of F is equal to F of 1 by 2. Now we know by fundamental theorem of ring homomorphism that R by kernel of F, here our R is C of 0, 1 divided by kernel of map is theta, so it is kernel of theta is isomorphic to R, right? So we know that if theta is a ring homomorphism from this to this, then C of 0, 1 by kernel of theta is isomorphic to R dash. Now we will find the kernel, right? Now we will find the kernel of this map. Now we will find the kernel of this map. So what is the kernel of this map? Now we will prove that the kernel is nothing but F of 1 by 2. Kernel is nothing but F of 1 by 2. So we will find kernel of theta. So kernel of theta is nothing but it consists of all those functions. It consists of all those functions which vanishes at 1 by 2, right? Because our map is F of 1 by 2. So kernel of F is kernel of theta is, so for we need to find kernel of theta. This implies theta of F has to be equal to 0, right? Theta has to be equal to 0, that is F of 1 by 2 has to be equal to 0. So kernel consists of all those functions which vanishes at 1 by 2, which is nothing but M. because our M is set of all functions which is matches at 1 by 2. Right? Our kernel is nothing but M. Our kernel is nothing but M. So therefore, kernel of theta is equal to M. Kernel of theta is equal to M. So therefore by 1 C of closed interval 0 comma 1 by M. Our M is the kernel, because kernel is equal to M is isomorphic to R dash. So therefore these two are isomorphic. Isomorphic means if this is a field, this is also a field. Sorry, this is not R dash, this is R, right? It is a real number, defining R. So therefore these two are isomorphic. So since R is a field because we know the real number is a field, right? Real number is a field. Okay, we know that this is a field. Therefore, since these two are isomorphic, C of 0 comma 1 by M is a field. So this means M is a maximal ideal. So we know that R by M is a field if and only if it is maximal ideal. So therefore M is maximal ideal. Now what I am going to I just do a recap of what we did. So we need to show that this set is maximal ideal. So for that what I am doing is I am going to use a theorem. This will be maximal ideal if R by M is a field, that is a quotient ring formed by R by M is a field. So for that define a map theta from C of 0 comma 1 to R defined by theta of f is equal to f of 1 by 2, and this is a ring homomorphism which we have verified. After proving that we need to find the kernel of this map, and we have found that kernel is nothing but the set M. Therefore C of 0 comma 1 by M is isomorphic to R because we have defined a map from this to this. So since R is a field, this has to be a field. This has to be a field, then M has to be a maximal ideal. That's it, right? So we have proved that it's a very important problem, right? So for example, if they changed f of 1 by 3, f of 1 by 4, f of anything, you have to just replace 1 by 2 by whatever the number they are giving. Now we will move on another problem. Let R be so this is another exercise problem, again very interesting problem. So again it's an exercise problem. So let R be the field of real numbers and S be the set of let R be the field of real numbers and S be set of all polynomials. S is the set of all polynomials fx which belongs to Rx, right? Rs means a ring of polynomials that satisfies the condition such that f of 0 is equal to 0 and f of 1 is also equal to 0. Prove that S is an ideal of R of x. Prove that S is an ideal of Rx. Prove that S is an ideal of Rx, and is Rx by S is integral domain, right? So this will be integral domain if S is prime ideal. S is prime ideal. So for what we need to do is we need to check whether it's an ideal, and suppose if this is a prime ideal, then this is true because Rx by S will be an integral domain if and only if S is prime ideal, and this will be a field if and only if S is maximal ideal, right? Therefore Rx by S is integral domain. Is R, they are asking, right? There is a question mark here. Is R by X by S is integral domain? So we need to check whether S is ideal, and if it is ideal, we need to check whether it is prime ideal or not. So what is S? S consists of all those functions in Rx such that f of 0 is equal to 0 and f of 1 is also equal to 0. For example, f of x is equal to x minus x square. This will be in this set, because if you put f of 0, it is 0 again, f of 1 is also 0, because 1 minus 1 is 0. So this function will be in this set. So this set consists of all those functions. Remember, it is a polynomial, it is not a continuous function. Actually, polynomial is continuous function. So it consists of all those functions in Rx such that f of 0 is equal to 0 and f of 1 is equal to 0. Now first we need to check it is an ideal. First we need to check it is an ideal. So what is the first we need to show that S is ideal. Show that S is an ideal. So ideal we need to check 3 conditions. The first is you just take 2 element AB belongs to S, then A minus B should be in S and AR and RA should be in S. That is the condition for left ideal and right ideal. So AB belongs to S means A minus B belongs to S. So let us take 2 elements in S. That is, we need to take 2 functions in S, because S is the elements are functions here. Let us take 2 functions. Okay, let us take f of x and g of x belongs to S. That means f of 0 is equal to 0, f of 1 is equal to 0, g of 0 is equal to 0, g of 1 is equal to 0. Now we need to show that f of x minus g of x also in S, right? F of x, okay. So let us take h of x is equal to f of x minus g of x, right? Let us take h of x to be equal to okay, we will let us take, actually this is a condition for ideal. Let us take f of x and g of x belongs to S. Now let us define h of x. Let us define h of x as f of x minus g of x. We need to show h of x belongs to S. We need to show h of x belongs to S, because if A be in S, A minus B should be in S. A minus B is f of x minus g of x. I am naming that as h of x. So we need to show h of x belongs to S, right? Yes. So we need to show h of x belongs to S. Now what is h of 0? H of 0 is f of 0 minus g of 0. And what is h of 1? So it is f of 1 minus g of 1, which is nothing but 0, because f of 0 is 0, g of 0 is 0. Why? Because we are taking fg in S. So if fg in S, then f of 0 is 0, g of 0 is also 0. Therefore this is equal to 0. So we have h of 0 is equal to 0, h of 1 is equal to 0. We have h of 0 is equal to 0, h of 1 is equal to 0. That means h belongs to S, because we are having a function that satisfies this condition. So what is h? Our h is f of x minus g of x. So therefore I have taken 2 elements in S and then I have proved the difference of the elements also in S. So therefore this is the first condition for ideal, that is it satisfies, that is it is a subgroup. It is a subgroup. So we have proved the first condition. Now we need to prove the second condition. So for second condition is if A belongs to R and let us say it is R, and if S belongs to S, we need to show RS belongs to S and SR also belongs to S. This is the condition for left ideal and this is the condition for right ideal. Now okay, now we will prove this, right? This is a condition for left ideal. So for that what I am going to do is, I am going to take an element f of x in S and I will take an element r of x in R of x, right? So I am taking one element in S, I am taking one element in ring R. I need to show that product of 2 elements is in S, right? Yes. Now I am going to define another function which is t of x. So I am going to define t of x as f of x into r of x. I need to show that t of x belongs to S. Now what about t of 0? So t of 0 is f of 0 into r of 0 and t of 1 is f of 1 into r of 1. This is 0, this is 0, because f of 0 is 0, 0 to anything is 0, f of 1 is again 0, 0 to anything is 0. So we have t of 0 is equal to 0, t of 1 is equal to 0, that means t belongs to S. So what is t? So t is f of x into r of x belongs to S. Therefore it is an ideal. Therefore it is an ideal. So therefore we have proved that the set of all those functions which vanishes at 0 and 1 is an ideal. Now we need to show is Rx by S is an integral domain. For that we need to claim that whether we need to check whether it's a prime ideal or not. If it is a prime ideal, then this will be an integral domain. Suppose if it is not a prime ideal, this will not be an integral domain. This will not be an integral domain. So we will claim that S is not prime ideal. So what is the definition of prime ideal? So for prime ideal, AB belongs to S, A belongs to R, B belongs to R, A belongs to R, B belongs to R. This implies either A belongs to S or B belongs to S. So this is a condition for prime ideal. Now we will show that it is not prime ideal. We will show that it is not prime ideal. So it is enough to give a counter example to show that an ideal is not prime ideal. So we will show that S is not prime ideal. So for that, what we will do is, let us take a function f of x is equal to x into x minus 1. This belongs to S. Why? Because f of 0 is again 0 and f of 1 is also 0, because 0 into 0 is 0, 1 into 0 is again 0. So therefore this belongs to S, right? So f of x is equal to x into x minus 1. Okay, thus f of x belongs to S. Now let us take P of x, let us take some element P of x is equal to x, and let us take Q of x is equal to x minus 1, right? Now you can see this also satisfies so this is a condition. You just take two element in R. So what I am doing is okay, I will do in more convenient way. So I am going to take, I can choose A, B in R. So here R is the field of real number, here R is the okay, what is R here? Okay, so AB belongs to S means either A belongs to S or B belongs to S, right? This is a condition for prime ideal, right? Yes. Okay, so let us take f of x. Okay, we will do as it is, x into x minus 1. This belongs to S because this belongs to S because f of 0 is 0, f of 1 is equal to 0, right? Now let us take P of x. P of x equal to x. P of x equal to x. Whether this belongs to S, not. Actually, this will be in S if P of 0 is 0 and P of 1 is 0. But here P of 0 is 0, but P of 1 is 1. Therefore, this does not belong to S. Now, what about Q of x? Q of x, let us take Q of x to be equal to x minus 1. Again, this does not belongs to S. Actually, Q of 1 is 0, but Q of 0 is not 0. Therefore, both are not in S, right? But x into x minus 1 belongs to S. So, if we know that AB belongs to S means either A has to be in S or B has to be in S. But here we have x into x minus 1 belongs to S, but x does not belongs to S and x minus 1 also does not belongs to S. That means not prime ideal, right? It's a very easy problem. So I have defined a function x into x minus 1 as x into x minus 1. So this does not belongs to S, this does not belongs to S, but the product belongs to S. The product belongs to S means one of them should be in S, but here none of them is in S. Therefore, it is not a prime ideal. It is not a prime ideal. So since it is not a prime ideal, R by S is not integral domain. This will be an integral domain if and only if S is a prime ideal. Therefore, it is not integral domain. Right. So you take this exercise, page number 369. So give an example in which prime ideal is not maximal ideal. So every maximal ideal is prime ideal, but every prime ideal is not maximal ideal. So what they are doing is they are giving a set. So Yeah, this is also a very important problem. So, just refer page number 369. Krishna series consists of book for detailed proof. It's a one page proof, but it's an easy proof. It's a lengthy proof, but it's an easy proof. So, what they are doing is they are taking Ix with a ring of polynomials with a ring of integers. So, they are taking Zx and S be the principal ideal of Rx generated by X, and they are taking ideal to be the principal ideal generated by X. They are taking R to be equal to the polynomial ring over integers, and they are taking S to be equal to the principal ideal. Principal ideal means it can be generated by single element. So, they are taking the principal ideal generated by S, which is X. Now, we will show that we will show this is a prime ideal. This is a prime ideal, but not maximal ideal. Right. So, what is S? So, S consists of, S is the ideal generated by X, that is it consists of all those members X into f of X, and this f of X belongs to Zx. So, this set is a prime ideal, but it is not maximal ideal, Maximal ideal means there is some other set which properly contains all those functions generated by X. So, we need to show, first you need to show that the set is an ideal. So, for that you just take two functions and then you show the difference of that is in S, and then you show that is left ideal. For that you need to show AR belongs to S and RA belongs to S. It's a very easy process again, and then you need to show it's a prime ideal. So, for prime ideal again same condition, AB belongs to S means either A belongs to S or B belongs to S. Now, we need to show it is a we need to show that this is a not maximal ideal. So, not maximal ideal means we need to find some other ideal which properly contains S. So, we can find an ideal. We have X is properly contained in X comma 2, right, X comma 2. So, now we will show that X is not maximal ideal. For this we must show that ideal n of X is properly contained in I, while n is itself properly contained in X. Now, n of X comma 2 serves for this purpose. So, you need to verify, well, you need to know what is meant by X comma 2. You need to know what is meant by X comma 2, that I will tell you now. Okay, right, X comma 2, it's a higher degree polynomials, right. So, X comma 2. Now, actually it's a very easy process. X comma 2, I have left that page. Actually there is one term for X comma 2. So, there is page number, it will be in page number 350 something, right. So, we will show that this ideal is properly contained in X comma 2. That means this is not maximal ideal. So, therefore, we have given counter example to show that this actually you can refer page number 369 for detailed proof that this ideal is a prime ideal, but it is not maximal ideal. For the next video, I will start Euclidean domain, and then you will finish the syllabus, right. So, only thing that left is Euclidean domain, which I finish in another one video, right. So, that's it. Thank you.